protons will overlap. Any questions so far about the number of signals? All right, let's see if we can solve some of these spectra. And I got the screenshot so we can pull that up if we need a reference. I have to erase all this stuff first. All right. So let's go to the first spectrum, which is here. It's got 4 signals. And we said that, can y'all see that? My little window? Yes, no, maybe.
I don't see a little window, but I do see your screen
You see
with the
it?
graphs.
Yeah. But do you see the, uh-oh. Shucks. All right, can you see the small window? Why did I do that? Right here, where if I pop this up,
Moving away.
Yeah.
Yes.
Yeah.
it says snipping. All right.
Yeah.
Okay, that's gonna be our reference. Because I don't want to keep having to scroll back to the first page. So which one of these did we say was gonna give 4 signals?
Number 1.
Number 1, and we said this one could possibly give
Number 1, number 2.
1
That
and
one was like 3 to 4.
Number 4.
1 and 3, right? If we count the OH protons. Is that right? Otherwise, you said this will give 3. Yeah. And then we said this one will give 4. Yeah. So let's look at this one and see. We got 1, 2, 3, 4 signals. And then well, I don't know if I can draw it on here. Yes, I can. Oh, come on, little bootleg pen. So we got this. I should draw with the pad. Is that right? And let's see if we can solve it. Might want to put the oxygen back here. All right. Which one? What do you think? Look at the integration, right? You have this signal is integrated for 2. This one is integrating for 3. This one is integrating for 2. And then this one is integrating for 3. What do you want to start? Downfield or upfield?
Up.
Upfield. Okay. So what do you think? Where do you think this triplet is coming from? Keep in mind, this is a CH3. You have to bear with me on this drawing. This is a CH2. This is terrible.
From the CH3.
From this one?
Yes.
I agree. It should be a triplet, and it should be upfield because it's a typical, like an alkyl type proton. All right, let's go to the next one. What do you think? You can see that the lines here, 1, 2, 3, 4, 5, 6, right?
It's the 2 hydrogens next to the CH3.
This one. I
Yeah.
agree. Because you got 2 neighbors on this side and 3 on the other side. So that means you got a total of 5 neighbors, right? And so if you got 5 neighbors, then n plus 1 should be 6 or sextet. And we do see that. All right. Any questions about that one? What about the singlet? What do you think?
The CH3 by the oxygen.
This one?
Yes.
Why is it a singlet?
Because there's no neighboring hydrogen.
There's no hydrogens on this carbon next door. That's absolutely right. All right. What about the last triplet? What do you think?
The other two H's.
Right here.
Yes.
So this is for that. Is that right? This right here will be for here. And this is going to be the sextet here. And then this CH3 is going to be here. Can you see how the integration kind of helps to solve it too? Right? You got the integration, those numbers right over the signal. That's telling you how many protons each signal represents. And then the infrared, which is down here, right? What you would look for in the infrared is a couple of things. You'll look for this right here. That's alkyl stretching in the infrared. And then you'll look for this, right? That's a typical carbonyl stretch. So if you have a carbonyl present in your molecule and you take an infrared of it, you should see this stretch right here, right? And then the carbon-carbon chain, that shows up here. And it looks the same every time. It's like a kind of a jagged looking strong stretch or a medium stretch. All right, any questions about this one? No? All right. Let's see if we can move on to the next one then. And I'll just throw in the infrared information as, as a bonus. All right. Let's go to the next example. How many signals do we have here?
4.
3.
1. So 1, 2, 3, 4 signals. And we had, where's my little, can y'all see my snipping, the snipping box?
Yes.
Yes.
All right. So you see here where we said if the OH showed up, this would also give you 4 signals. Is that right?
Yes.
So 3 here. So 1, 2, 3, and then the OH is 4. All right. So how can we tell if this is, what's the difference in this spectrum and the other spectrum that we looked at up here? Because that gave 4 signals too, didn't it?
Yeah.
But based on the structure, we expect one of these signals here, pull it back up. We expect one of these signals to show up pretty far downfield. Is that right? Because you got,
Because it's by the oxygen. Because
because
of the
it's,
OH.
yes, exactly right. It's on the same carbon that the OH is on. So we expect these to show up pretty far downfield. And we can figure out the splitting pattern as well. Remember, the OH, even though it's a proton there, it will not split with the neighboring hydrogen. So what should this signal be?
Singlet.
What about the proton that's here?
Oh yeah.
Yeah, so there's a proton right there, right? So N for this one is going to be what? 1.
1,
So N plus 1 will be what?
2, doublet.
So it should be a doublet. And we can see based on what we know about OH it's called a carbonyl proton, but what we know about protons that show up that are on carbons connected to oxygen or sulfur or any other heteroatom is that they show up somewhere between 3 and 5, right? So we can see a doublet right here at 3.4, and it integrates for 2 protons. So we know that that's the right one. So I'm gonna try to redraw that. So this is an OH right here. All right. So we've already assigned that one. What about this doublet down here that's integrating for 6 protons? What do you think?
Methyl group.
It's the methyl groups over here, right? The branched methyl groups. Right, both of those are going to fall under the same signal. Why is it showing up as a doublet? What do you think?
Just one neighbor.
It's only got one neighbor right here, right? And so this will split with that and give you a doublet. So with this one, but you're not going to see two doublets because the protons are equivalent. So this is coming here. That's the signal for that. Then we only got one signal left, right? Well, the OH is here. You can see that that's integrating for one proton, and it's all the way down here, downfield. All right. Now this signal, this signal right here, this proton. What do you think?
Yeah, it's gonna be the last one because it has 6 neighboring.
It's got, well, does it have 6 or 8?
It has 7 neighboring, but isn't it 1 + 1? So 8 gaps.
Well, it's got 3 here, right?
8 neighbors.
3 here, and then on this carbon, that's a CH2. So it actually has 8 neighbors, right? So the N + 1 for that should be what, 9?
Mm-hmm.
Yes.
So N, that's not an H. +1 is 9. I feel like a kindergartner using this mouse pad, right? So let's count them up. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Following? So do you see, I hate that we didn't really cover nomenclature in part 1, but that's a typical, what you call an isopropyl type proton. You see how it's got 2 branch methyl groups around it, and the proton is right here. Right, that's an isopropyl type functional group. And so knowing that splitting pattern is common for that functional group. Never mind. Right, so that's an isopropyl type protein. It's always going to show up as a multiplet, and it's always going to show up somewhere between 0 and 2, right? Because it is a typical alkyl proton. All right. Any questions about that one?
What is that splitting pattern called?
What is this called? Well, you can call it a nonette because it's 9 lines. But normally anything over 6 lines, you just call it a multiplet. All right. Any questions about anything?